Hi everyone, my name is Julia Sveen and I go to FSU. And this summer I had the opportunity to work on a project on power supply failure detection using machine learning models. And my mentor was Dr. Yulia Smith and my co-mentor was Abby Centers. Okay, so just as an introduction, power supplies at the DC field facility are absolutely imperative for magnet operations, and if one fails, it can interrupt experiments and lead to major facility downtime. So these failures usually show up as abnormal behavior in two different signals. So you have the Q drive signal, which is the current, and you have the SCR drive, which is the voltage, and they are typically correlated. So we found that when a fuse is blown, that correlation breaks down, and we can capture it by looking at the slope of their difference or the derivative. So if you look at figure one over here, you can see normal behavior of these two signals, and they're correlated. Oops. And if you look at figure two, you can see that the Q drive drops significantly and the derivative rises significantly in effect. So the problem is that this data is very at high frequency, so it's not practical to monitor manually. So that's why we want to train machine learning models that are able to automatically flag early signs of failure. So our goal is to test different anomaly detection methods and compare their reliability, accuracy, and ability to run in real time. So for our methods, we tested three different models using only normal data for training, and so that way that anything as flagged as different would be considered anomalous data. So our first type of model that we tested was called a one-class support vector machine, or OCSVM. And the way that it works is that it draws a boundary around normal data and therefore flags anything outside as anomalous. Our second model is called an isolation forest model. And the way that that works is it splits the data randomly, so anomalies get isolated more easily. And then the third model that we tested is called a long short-term memory autoencoder, or LSTM model. And the way that that works is it's a deep learning model that learns to reconstruct normal patterns. And if something isn't reconstructed well, it's pretty clear that it's anomalous. So the way that we set up everything is we pre-processed all the signals by scaling and downsampling them. And then we trained and tested the models on a mix of normal and event data, and including nearly 9 months of worth of power supply data, which my mentor and my co-mentor very graciously combed through and prepared for me. Okay, so here are the results of what we found. So the OCSVM model detected failures, but was very sensitive to outliers, specifically in the normal data, which led to many false alarms even after fine-tuning the model and certain parameters in that model. The isolation forest model generalized better than the OCSVM model and achieved perfect accuracy on our small subset of event data. So not 9 months worth, but more around the lines of 3 months, I believe. But it was clear that the LSTM autoencoder had the strongest overall performance. So as you can see on the full event data set, it achieves an F1 score of 0.997, which is kind of an accuracy score, with only 4 false positives remaining after filtering, which is a huge reduction compared to the other models. And then on the actual normal test data, it reached a perfect F1 score of 1, with 0 false positives left after filtering, which was great. And what these results show is that deep learning models such as LSTM can provide reliable low noise anomaly detection, which is very ideal for high frequency systems such as this one. So where do we go from here? So the LSTM model is already showing strong results, and the team at the MagLab will continue working on integrating it into LabVIEW, which is the software that controls power supplies in real time. They're also looking to connect the model to Slack so it can send automatic alerts the moment an anomaly is detected, which helps the lab respond more quickly to potential issues. Going forward, the team will keep testing on larger data sets and keep refining the model to make it as accurate as possible and reliable as possible for long-term deployment. Thank you.